Hi and welcome. My name is Ulf Holmberg. I'm a PhD economist, hugely interested in the nature of consciousness and doing research on the side on this matter. And I'm going to present a recent study of mine, which I call Validating the GCP Data Hypothesis and Harvesting its Data. So let me begin by discussing what I have done and what I have found. So the hypothesis motivating or behind the Global Consciousness Project is that events which elicit widespread emotion or draw the simultaneous attention of a huge number of people may affect the output of hardware-generated random numbers in some statistically significant way. They can be picked up. And in this study, I find quantitative evidence supporting this hypothesis by applying time series statistics, looking at two seemingly unrelated data sources and finding correlations that are very supportive of the GCP data hypothesis. I then use these findings in order to construct something that I call a global attention index, because the significance of the results motivates that such an index could be constructed. And I'll present such an index in the end of this talk. So let's begin by talking about the Global Consciousness Project. Well, it is motivated, or was motivated, by the idea that research showed that the mind could stretch out beyond our heads and affect matter at a distance. There was a lot of study going on in the 1990s, and the end of the 1990s, the Global Consciousness Project was initiated, and it has produced data ever since 1999 up to date, and based on 70 physical random number generators spread out all over the globe. So the idea then was that these random number generators would be affected by emotions, by global interesting events, and up to date, the project has actually produced remarkable results. Even so, the results are often criticized. And they are criticized because they are controversial. Such a mechanism that the mind actually can affect matter is not part of the standard model in consciousness research. It's not part of the standard model in neuroscience either. In fact, the prevailing working hypothesis in most sciences is that the brain produces consciousness, that consciousness actually is the epiphenomena of complex information processing patterns. So the mind is nothing, has no ability to affect matter at a distance. It is also very controversial when it comes to physics, because it's not part of the standard model there. And in fact, the GCP data seems to violate some well-established rules in physics. In particular, the second law of thermodynamics, their rule on entropy. Because here we have random number generators producing pure random numbers. So that's the kind of endpoint in the entropy process. And if you could change that mechanism by only the intention alone, that is adding order into chaos, which seems to be a violation of the second law of thermodynamics, at least the way it is understood to date. Finally, the GCP data hypothesis results seem to is accused for cherry picking. So they only pick events that kind of goes with the idea of the GCP data. So the idea here is there's going to be intraday movements that looks like trends. And if you only look at, if you find such a trend, you will always find a date or an event that fits into that date. This last criticism is something that actually can be studied is that really true? Because how the criticism can be addressed by looking at if the hypothesis holds true, the data should covary with other variables affecting global attention and intent. So there are loads of variables out there that are affected by attention and intent, and in particular stock markets are affected by global attention and intent to the workings of daily movements. And in a study I made in 2020, published in the Journal of Consciousness Studies, I actually showed that a daily aggregate constructed out of the GCP data, a daily aggregate, I call the max Z, significantly correlates with global stock market returns. And in the picture you can see here below, the whole idea is that there is probably some statistically larger quantity affecting two seemingly unrelated data generating processes. One process generating stock market returns and one process generating GCP data effects. Now, if the GCP data is pure random, there will be no correlation. There will be nothing saying there will be an intersection. But if there is an intersection, there is probably some true larger quantity affecting both DGPs at the same time. That was exactly what I found in the previous studies, but in this study, I go even further and test for how several different GCP data aggregates interacts with global internet search trends. And then I use the fact that engaging world events seem to attract the need for information. The most recent example of this is when the coronavirus and the pandemic hit the world. Nobody really knew what it was. So people start Googling it. And if people start Googling it, searching for information, it is picked up in Google search trend data. So I'm going to use changes in an index right out of Google search data and try to correlate it with GCP data aggregates, because I'm going to say this is probably going to be a proxy of it. So there should be a testable intersection on the changes in Google search data and on the changes in GCP data aggregates. If there is such a thing, there's probably some other mechanism affecting both data generating processes. Okay, so looking into the Google search data, I use products or a free product they call World in Search every year, or a year in search. And I pick out the 5 most searched for words every year back to 2014. And I use 2014 because that is the year when this particular product was made publicly available by Google. And as you would see, the events here are rather familiar. Like 2020, coronavirus and election results were the 2 most searched for words globally. In 2019, Copa America and Notre Dame were the 2 words most searched for. And in 2018, World Cup, Hurricane Florence, and so forth. So I do not discriminate with importance here. I say all these events are engaging in one way or another. And I say, I'm not going to give any weight to them. They're all equally important. I will, however, add 3 additional search words to my search index. And that is earthquakes, hurricanes, and shootings. And that is because if you look into the data and even further back in different countries and so forth, you can find that natural disasters and random acts of violence seem to be engaging events. So I add these 3 extra search words to this list of 5 search words per year. Then I collect data going back to 2004 and construct the search word index. The search word index is rather easy, actually. It's a sum of these individual index values. So Google then provides a search word index on each search word, and with the highest value on the high is when the search word was searched for at the most throughout the full period. So obviously then when you add more events over time, it increases in volatility. that is what you would see from 2014 and going onwards. There's much more volatility there when you add more events, but it's rather similar, or easy at least. So then we have at least one of these data sources. We have the Google search index. Now I only need to look at changes in the GCP data aggregates, or at least get the GCP data aggregates on a monthly basis in order to test for this intersection. And I do this by looking into the GCP data's second by second random numbers, which they make publicly available on their website. And then I use their 15 minutes chunks, which is also made publicly available, and the Z scores, which are calculated according to the equation you can see in front of you. Now, from these 15-minute scores over the course of 24 hours, I derive the daily minimum, the daily average, and the daily maximum. And important to note here is that the underlying statistical properties of Z is actually known. So you can think of it as the absolute value of a standardized random variable, one could say. So you can use these statistical properties in order to derive statistical measures, actually, which I will use later on in the index. But anyways, so here's the daily aggregates as they look, and they are very noisy. On the upper side, the purple is the max Z variable, the one I used previously to correlate with daily stock market returns. The average Z is the blue in the middle, the bluish, and the min Z, the one with the least action, is on the bottom. Importantly to note is that there are occasional large increases in all three aggregates simultaneously. In particular, this is in the beginning of 2020, when the min Z started to increase, the average Z, and the max Z. Now, so that the average co-varies with the minimum is not that surprising, but that the maximum actually does is something that should be studied further, but I haven't done it yet. But I just make notice on these movements and I say, okay, so you can probably use this that looks like noise and construct monthly GCP data aggregates by simply averaging it out. So if you take the monthly average on each of these series, you get series that looks something like this. Also here, looks purely like noise, more or less, with some occasional jumps here and there, which we can look further into later. But these are actually very important in the construction of the global attention index, which I'll be discussing later in this presentation. So now I have the GCP data aggregates that I want to correlate with the Google search index. And doing so, I present 5 different models on the estimates on changes on this SI index and including the GCP data aggregates. Now, I don't want you to focus on the numbers per se. I will just start by looking on model 1. Model 1 is a univariate model in that sense that the change in SI is only dependent on itself. So I try to look at, so what is the best univariate model to explain this series on its own? It looks like attention seems to last for about 4 months, and then we lose interest, whatever you want to call it. So, but that's the best fit. So you have a particular topic, people start Googling on it, for 4 months' time, you have an increase in interest in it, and then that interest fades away. In model 2, 3, and 4, and 5, I include the GCP data aggregates. And in particular, in model 2, I use the minimum Z. In model 3, the average Z. Model 4, the max Z. And in model 5, I use all 3 GCP data aggregates simultaneously. You can't see it in this table, but I test the goodness of fit for this model. So the idea there is, does including these variables reduce the randomness in the model, and they do. The goodness of it increases. So, but now focus on the value in parentheses and begin with model 2. So you would see there's 0.015. That says that the p-value is about 1.5%. So this suggests that the probability that this particular variable adds is just that this significance is found due to chance is about 1.5%. That's roughly speaking what it says. Go to the average Z, the probability of actually being due to chance is so low that it has to be approximated with about 0. So it's very, very significant. And if you look at the max Z, also this one is significant at the 5% level because a 3.2% probability that it is due to chance. But in model 5 then, when you include all three at the same time, the min and the max become insignificant while the average remains weakly significant at about 5% level, which is rather expected because an average would always include the minimum and the maximum. So in that sense, it kind of validates the other results. All right, so let's take a step back. What does these numbers actually tell us? Well, it tells us that the GCP data hypothesis is most probably true, because here we have one source of data, the Google search index. Arguably, this springs from a different source than the GCP data aggregates. And now we have two seemingly unrelated data sources that correlate very, very significantly. And it can only do so if it's spurious regression. That could be true. And spurious regression actually refers to that there is some unknown entity affecting both variables at the same time. And that is kind of what you claim to be true. It would be consciousness. Okay. So that's kind of validates the hypothesis. Now, the good thing is that now we know that the average Z correlates very significantly with Google searches. That was the one with the correlation, the probability of being due to chance, it could be approximated with 0. So you could probably say that standardized average Z values can be used as a proxy for global attention. Okay. Then you can filter and smooth the daily data by applying the one-sided Hodrick-Prescott filter on the standardized average Z variable. So this is how it's done. Firstly, assume that the average Z variables, which I call Y now, can be broken down into 3 subcomponents. The first one is a trend component, as I call tau. The second one is a cyclical component, which I call C. And then there is a pure random process component, which we call epsilon. So the sum of these 3 will then produce the average Z value at time t. Now, the good thing is that you can actually apply this formula, which I'm not going to go through in detail, to be able to minimize, you find the smallest value of tau that actually to get this the smallest tau value that satisfies this equation, and then you'll get the trend variable, which I then will call the global attention index. So let's do this on the daily data and the monthly data, and you will get something that looks like this from 2004 and onwards. The solid line is the daily attention index, and the dotted line is the monthly attention index, and they've constructed out of the exact data used in the regressions that I showed you previously. And as you would see, they tend to vary jointly. Now there is a line which I call a threshold, and if you might recall that I said it's good to have this idea of the statistical properties of the underlying data, because if you standardize it, then you can say, okay, so if you pass this level, this is probably not due to chance. And that is what this line says. So if the index values passes the threshold, it seems very unlikely that the increase is due to chance. So then you can find that there's particularly 4 interesting periods since 2004, which probably needs some analysis to look into, which I do in my paper. But I don't have time to go into each of them individually. But you can look at them and say, okay, this one was probably this, and this one is probably that. But I would focus on this particular event, the beginning of 2020. So let's zoom into that part here. It looks something like this. The solid line now is the attention index, and it's measured on the left-hand axis. And on the right hand, you would have the average Z, which is the underlying variable used to construct the attention index. Now, what could have caused this increase? Well, it's not a wild guess to say could it be the onset of the COVID-19 pandemic? Well, let's look at it. On the 12th of January, China publicly shared the genetic sequence of COVID-19, and people were getting affected and getting worried. It was about this time that Taiwan was thinking about closing down its borders as well. On the 13th of January, COVID-19 had spread to Thailand, and on the 19th of January, China confirmed that the new coronavirus, which later called COVID-19, spreads from humans to humans. And as you would see, then the attention index was hugely elevated. Notably, this is a couple of months before it got grips of Europe or the US. But in any case, you would actually see the onset, at least, being found during the attention index. Going back to the attention index, you will see there is also a second one, maybe in 2020 and the end of 2020, perhaps due to the beginning of the end or due to second wave, third wave, or whatever. This needs more research. But you could probably say that, at least indicatively, this seems to fit the world events rather nicely. So I will have some concluding thoughts as well. So the GCP data, the aggregates of it, covaries with the search word index derived from Google's trends data. The Google's trends data index that I've been using is very rough, could probably be refined, and so are the GCP data aggregates, the monthly. So I'm guessing that this correlation found, the significant, could be even strengthened even further by refining the index measures. Anyways, this is very significant. So the results validate GCP data hypothesis. I also claim that this found dependence motivates the construction of a global attention index, which I construct, and I show by example that it seems to be able to pick up the engaging world events. But the question is how and why? Why does the mind have the ability to actually affect matter at a distance, or at least feelings, and how does it work? As I said, it is not part of the standard model in neuroscience or consciousness research. In fact, that way, the mind is only the byproduct of the information processing patterns of our brains. But yet these results are very significant. So maybe one needs to look elsewhere. There are, of course, alternative theories of consciousness that could play a role in explaining this. One is the electromagnetic field theory, and one is, but the electromagnetic field produced by our brains will most probably not be strong enough to affect random number generators so far apart as these are. Maybe one has to be starting discussing alternative theories instead. Perhaps it is a consciousness field laying out there, and emotion and intent or attention produces ripples in that field that actually affects matter at a distance, or maybe attention on its own produces some sort of field that affects these random number generators. Whatever its cause, I would say that these results suggest that most researchers with regards to consciousness needs to take the GCP data seriously and start thinking about alternative theories or mechanisms that could explain the workings. Thank you for listening.